Welcome to today's lecture. We will continue our discussion on application of fluid inclusion studies of fluid inclusion microthermometric data to understand deformation in crustal rocks. So, in this context, as I told before, we could always look at many of the examples of the work that have been done in the Indian context, and I would like to cite one piece of very interesting piece of work that was done on the great boundary fault by Srivastava and Sahai, and here we get to see a very good example of how fluid inclusion data has helped in making some important conclusion about the progress of deformation in this particular major crustal structure. So, this great boundary fault, as we know, is on the juncture of the Aravalli Craton and the Vindhyan basin, and it has got a north north east south south west type of a trend, which I am not showing here, and the details of it, the geology of it could be obtained from this particular reference or from standard textbooks. So, this great boundary fault was studied by these authors on its south or the southern extreme, where it is actually juxtaposed against the Vindhyan sediment and the basal Vindhyan group of rocks, the Coimbatore sandstone, where these structures are developed. And so, the analysis of this evolution of this great boundary fault is generally understood to have taken in this way. Initially, there has been this particular boundary fault has been reactivated more than once. The initial type was a thrust type, and was followed by a strike slip type, and again followed by a thrust type. So, we know that this actually again it is a situation where the principal stress axis is horizontal. It is a compressive stress axis that is acting upon, which just the changing over of the intermediate and the minimum principal stress axis. In one case it gives rise to a thrust type movement, and the other it is a strike slip movement, and again changing over to a thrust type movement depending on the condition of the far field stress. Now, here the main boundary fault was studied in its southwest extreme. So, the first phase of thrusting with sigma 1 east west and the sigma 2, that is north south horizontal, and sigma 3 is vertical. So, when sigma 3 is vertical, we would expect that the movement will be of a thrust type. So, the pure deep slip thrust is revealed from. So, a good amount of structural analysis has been done by these authors, which I will not be discussing in details here. The second phase of reactivation was in conjugate shear zones and fault planes with horizontal strike slip movement. Here the sigma 3 is horizontal and sigma 2 is vertical, and it was followed by the third phase of axial extension. Now, this photograph which is shown here, taken from the authors, that they are the en echelon vein patterns, vein arrays in conjugate brittle ductile shear planes as a consequence of the second phase of reactivation, interpreted as due to the hybrid extensional shear and of the crack seal origin. These are the typical features which essentially are by the mechanism of crack seal process. So, these are the ideal sites. So, the fluid inclusion work of this particular work which I will be referring basically is is centered on these crack seal veins which are associated with the second phase of reactivation of great boundary fault, and are the ideal sites to look at the fluid inclusions and to see the fluid characteristics and try to see as to how much they would be helpful in understanding the deformation process. So, here these are the different arrays or the trails of the fluid inclusions interpreted to be the CFF, which is the cross fold fractures, the SF is the strike fractures, and the OF are the oblique fractures. So, So, these are the kind of conjugate set of fractures which are present in these veins and which could be studied. So, these veins, these arrays of the fluid inclusions contain mostly aqueous biphase inclusions which are interpreted to be NaCl, CaCl2, H2O type based on the eutectic temperature that was obtained during the freezing experiment. So, what is shown here is that the ranges that the authors obtained while doing the freezing and the heating runs, and where they say that the number of inclusions where the paired salinity homogenization salinity temperature data could be obtained were less, but that does not affect the outcome of the work. So, here the last ice melting has been presented, which we could see that they are of moderately high saline kind of fluid and are NaCl, CaCl2, H2O type, and the homogenization temperature ranges from greater than 210 to about 110 degrees Celsius or less. Now, these if these inclusions are taken all together, then the densities of these inclusions are calculated and the isocores of the inclusions, the total density ranges being covered with 0.9 to 0.1 are shown on this particular diagram, on a pressure temperature diagram as constructed by these authors. And as you could see that they do, so they represent the ranges of the pressure temperature conditions of entrapment of these inclusions. Now, as we know that the isochore themselves will not be able to tell us the conditions. So, the best alternate or the best option here is to see the geothermal gradient and then draw the geothermal gradient here and see the intersection point of the geothermal gradient with the isochore, and that would give us an idea as to what could have been the ranges of the fluid pressure during the formation of this or during this second phase of reactivation of this particular structure, the regional structure that we are talking about. Now, if you see here, then taking a normal geothermal gradient of 35 degrees centigrade per kilometer, which is actually translated as 1.32 degrees per megapascal. So, we could see that they would correspond to some 125 to 175 megapascal pressure. So, that value of 125 to 175, we could take an average value of pressure. So, it is around 129 to 175 megapascal pressure, that would indicate about 5 to 7 kilometer of paleo depth. Now, the situation is that here also the similar type of situation as we just discussed in case of the in orogenic gold mineralizing system, here also the situation is more or less the same. During the process of the initial phase of thrusting, there the fluid which build up the supralithostatic pressure, and then with the rupturing, then the strike slip movement, there the fluid pressure dropped, and it is kind of giving us the conditions of the pressure, the fluid pressure, and that would be translated to around 5 to 7 kilometer of paleo depth. Now, the situation is that these values of 5 to 7 kilometer of paleo depth would indicate that there are at least to be 5 to 7 kilometer of overburden to have been there during the time of this reactivation of this particular strike fault in the form of the strike slip movement. Of course, then one would like to look for whether there are evidence of existence of such thick overburden on this particular situation or not. It depends. If the available evidence support, then this could possibly be taken as the value of the paleo depth and the pore fluid pressure, and the interpretation could possibly be made in that way. Now, if there is a suspicion that there is no indication of or the evidence of having a 5 to 7 kilometer of overburden does not exist or is not feasible or tenable, then some alternate model has to be thought of. And suppose in this case, from various other consideration, it is possibly agreed upon that instead of 5 to 7 kilometer of failure depth or having overburden of 5 to 7 kilometers, it could have been just about 2 kilometers of overburden around that time above this the situation where the reactivation took place from the available geological evidence in terms of the sediment cover. So, in that case, what would agree to about a 2 kilometer of overburden? So, it can only be possible if the geothermal gradient, instead of being what is shown here as 35 degrees centigrade per kilometer, if it is as high as 67 to 88 degrees per kilometer, then only under the existing condition of the isocores that were constructed, then it is going to intersect the isocores at condition which will agree to about 2 kilometer of failure depth, 2 kilometer of. So, that would correspond to the pressure which is about 50 megapascal, and that would correspond to about 2 kilometer of failure depth in terms of lithostatic pressure. So, since there was no evidence of such thick cover above the horizon, that is the Coimbrous sandstone of Vindhyan succession, and no evidence of vertical movement. So, in addition to that, also there should be some evidence that there must have been some amount of vertical movement, so that the overburden of 5 kilometer could have been agreed upon. So, finally, it was interpreted as due to a much steeper geothermal gradient with evidence of about 2 kilometer of thick of overburden. Now, the situation is that so this would agree with the available picture of crustal evolution in that particular segment. So, such high geothermal gradient could only be possible if there is some kind of a rifting phase that is associated. So, the story goes like that: the normal faulting as a result of rifting, followed by building up of supralithostatic pressure and thrusting, that is vertical sigma 3, release of pore fluid pressure, seismic slip, sigma 3 becomes vertical resulting in strike slip movement, then the pore fluid pressure, and then again lithostatic pressure. So, this makes a very coherent and a consistent picture when the fluid inclusion data is integrated to whatever other information have been gathered from the structural analysis and from all other geological considerations taken together. So, this kind of geothermal gradient can only be is possible only if there is a rifting in that particular segment of the lithosphere. So, then this particular irrespective of whether this model is finally an acceptable model, or whether there could be some refinement done to it, or whether more of such evidence to be looked for to get a better picture of the evolution here, that is besides the point. But what is evident, or what is more important here, is that fluid inclusions have come up in a way in making some conclusions which are actually far reaching and are very important conclusions. That only reminds us of the fact that these objects may be tiny, but the conclusions drawn from the information obtained from them is great. So, that with that I will conclude the discussion on the application of fluid inclusions in broadly to be called as application in structural geology or understanding deformation and crustal evolution in many different. So, there are innumerable such work which can be seen in many different parts from many different continents by experts, and they will give us a good amount of information and idea as to in what way fluid inclusions can be utilized, fluid inclusion data can be used in conjunction with such kind of studies. Okay, so we will now get into a little bit of a discussion on the fluid inclusions in metamorphic mineral assemblages. I will not use the term metamorphic rocks, because after of course the rock is constituting of the mineral assemblages, and any particular mineral assemblage in a metamorphic rock is indicative of the physical process and also the physico-chemical process rather that operated in that particular segment of the crust. So, the fluid inclusion, it is also that the literature on the application of fluid inclusion studies to metamorphic rocks is also quite vast. To make an exhaustive review or to cite many cases, so they will also be very selective and only go by the very simple principle of how we can use the fluid inclusion data to understand metamorphism. It is very obvious that yes, if we see a particular assemblage of minerals, then out of those, and if we could establish that this belongs to this is an equilibrium assemblage corresponding to a particular pressure temperature condition, then we could always look for the minerals within this assemblage in which we could study fluid inclusions. The metamorphic minerals, as we have said before, of course quartz is always is a ubiquitous host of fluid inclusions, and fortunately is present in a wide diversity of mineral assemblages in metamorphic rocks as in many other crustal rocks. But then minerals like garnet, cordierite and many other metamorphic minerals, even sometimes they could be observed in pyroxene and other metamorphic minerals which actually nucleate in the process of metamorphism. We can study fluid inclusions in them. The fluid inclusions will of course be of the compositional type that we know of. They could be gaseous, I mean could be the mixtures of carbon dioxide or carbon dioxide plus methane plus sometimes nitrogen and argon, or could be aqueous inclusions, or could be mixed aqueous biphase inclusions. So, when we see the inclusions in them, so as we discussed before, when we were applying it to a particular area of geology, it has to be integrated with whatever information, independent information can be obtained from that particular study. For example, when we are looking at the metamorphic assemblage, we will use our concepts of phase petrology, and by the mineral chemistry, and then by using the concepts of equilibrium thermodynamics, we could have we could establish or calculate the pressure temperature conditions during which that particular mineral assemblage would have formed. So, there are many ways, many they are all expertise in the field of metamorphic petrology, which I am not coming to any discussion, but it is a fact that we could put some kind of limits to the deciphered pressure temperature conditions and can represent them in kind of a box. And we always talk of situations as a prograde or a retrograde path, and the prograde path would have progressed with changing of the mineral assemblages in a sequence when the higher pressure and temperature conditions are encountered. Earlier mineral assemblages through reaction giving rise to new assemblages which are stable under that particular pressure temperature conditions, and sometimes we talk of something which is a peak metamorphic condition, which possibly where the compositions are frozen there in the constituent minerals like say garnet or pyroxene, spinel, etc., and that particular situation is basically designated as the peak metamorphic condition. So, we need to work out, it is not only the peak metamorphic condition, but we always aspire to quantify or to work out the path precisely, whether it is a clockwise path or a counterclockwise path, looking for evidence of the minerals, whether there were some retrogression, some development, some of some reaction texture, some corona, some rim somewhere, and then try to complete the story. So, the basic idea here is that suppose we have a pressure temperature box defined by taking the mineral assemblages representing the peak metamorphic condition. Now, if we have either one or more than one mineral members of this particular assemblage, where we look for fluid inclusions and we see fluid inclusions as there in the form of primary inclusions, then it leads us to presume that well, there could be the fluid that were trapped during the peak metamorphic condition, and look at the fluid of what nature, what composition it is, whether it is a mixed aqueous carbonic type or a pure carbonic type or pure aqueous type. So, acquire the thermometric microthermometric data and then draw the isochore. So, if the isochore happens to pass through the PT box defined by phase petrology, then we kind of conclude that this represents the peak metamorphic fluid. That is what is the characteristic of the peak metamorphic fluid. If the isochore does not pass through the peak metamorphic conditions, if like for example, in this particular diagram which has been taken from Touré's paper, here again of course, whatever we have discussed in context of the situation corresponding to the preservation of the fluid inclusions when they are subjected to or they subjected to conditions which far deviate or are far different from what could possibly be dictated by an isochoric path. For example, if this is the isochore of this particular inclusion which was passing through the box, it will all the way down. If the pressure temperature conditions would have changed exactly dictated by the isochore, then there is no reason to suspect that this particular inclusion will not be preserved in its form the way it was entrapped primarily. So, Touré puts these kind of points here, that the intersection of the isochores and the PT box is definitely one of the prerequisites to really conclude that a particular fluid that we are actually looking at is the peak metamorphic fluid or not. Of course, the condition goes without saying that the inclusion must be primary in any of the mineral in the equilibrium assemblage. If they happen to be on their secondary or they are present in transgranular cracks, heel cracks, then the interpretation will be different. The composition of the fluid must conform to what is reconstructed from mineral fluid equilibria. This actually is a very intricate exercise, because if we write if there is a mineral assemblage in which we are able to write a reaction to be representing the particular assemblage. So, if that reaction happens to involve a fluid phase, then by working out the reaction equilibria and the thermodynamic considerations, we would be able to reconstruct the composition of the fluid in terms of the fugacity of the components that is present. For example, if it is interpreted to be a fluid which has been responsible or which was a part of the reaction of this mineral assemblage, where the fluid has definitely been entrapped as inclusion in these minerals which grew. So, it would be possible through that particular reaction equilibria to arrive at values of the fugacity of these constituents, say for example, water or carbon dioxide, and from that it could possibly be the composition in terms of the fraction or the mole fraction or the molar proportion of the different components could be established or could be estimated. So, that has to agree with the fluid inclusions which you are seeing, because we can analyze them by using some kind of a non-destructive microanalytical technique and can calculate the concentration of the different species. Even though we do not see that much of detailed work, but this definitely remains as one of the prerequisites for a particular inclusion to represent the peak metamorphic condition. So, in that, so here also it is discussed in the context of what exactly we discussed a few lectures before about their non-isochoric path of evolution of the rock or the mineral assemblages of this particular rock in the later part of its evolution. If it would have undergone an isobaric cooling or it would have undergone an isothermal decompression, and we also have fair idea as to what kind of distribution in the temperature of homogenization we would expect if it is an isothermal decompression or an isobaric cooling. And qualitatively this author has put kind of a limit like this. These two green lines represent as if like a safe corridor, means the inclusion is unlikely to be re-equilibrated or unlikely to be destroyed or its chemistry to be changed or the shape to be distorted if the pressure, suppose if this is the isochore, then it is kind of the deviation, what degree of deviation could possibly be there, so without actually destroying the inclusion. This of course will remain qualitative, but we know that when we are looking at by remembering the series of experiments on the re-equilibration of these inclusions, their deformation, their change in chemistry that we discussed, and we cited the experiments done by many experts in this particular area, that whenever there is an inclusion group of inclusions or an assemblage of inclusions and they are subjected to path which far deviates from their isochoric evolution, then there are always chances that many of those inclusions to survive depending on the size of the inclusions. And how exactly to look at the inclusions and to make interpretations and put the caution in our interpretation of our data if any such situations would have happened. So, in summary, when we talk about looking at fluid inclusions to understand the metamorphic environment or to understand, because we are more concerned here with the fluid, that the fluid chemistry or the fluid characteristics and what we can derive the intensive parameters like pressure and temperature. This we know that if we have we could get some kind of agreement when we construct. So, such kind of PT boxes could always be in a complete path of evolution where there would have been a peak metamorphic conditions, then would have followed by a process of retrogression, and if such mineral assemblages are also preserved in sequence within the same rock, then we can always study the fluid inclusions in such kind of different assemblages in the same rock. I would like to cite one important piece of work in this context, which was done in the Eastern Ghats metamorphic belt by Sarkar et al. This reference also is provided. I would, without getting into much details of the phase petrology part of it, we can still concentrate on what important conclusions were drawn from the fluid inclusion data. So, here we see that from phase petrologic considerations there were two different conditions which are deciphered. The peak metamorphic conditions which almost about 1000 degrees Celsius and about 8 to 9 kilobar, and they actually are represented as the ultra high temperature kind of metamorphism indicated by presence of spinel, and sometimes with also such kind of environments are also indicated by presence of minerals, pyroxene minerals such as sapphirine. And in this case the authors describe a spinel, quartz, iron titanium oxide, sillimanite and orthopyroxene bearing assemblage. Here has been shown by this reaction in the chemographic projection over here on the PT space, and this represents the peak metamorphic condition with mineral assemblage of spinel, quartz, iron titanium oxide, sillimanite and orthopyroxene, and the retrograde assemblage with garnet corona, orthopyroxene, and a second generation of quartz rimmed by spinel. So, this possibly was the ideal condition to study the characteristic of the metamorphic fluid, because we have quartz 1 and the quartz 2 in this assemblage, and they studied the fluid inclusions, and they report both the quartz 1 and quartz 2 to have been populated with pure carbonic inclusions, and these pure carbonic inclusions in the quartz 1, which is in the corresponding to the peak metamorphic condition, is of a high density, and the quartz 2, the same carbonic inclusions are calculated to be of lower density. I am not showing the histogram or the values of the depression in freezing point of or exactly the temperature of homogenization of the carbon dioxide inclusion. So, as expected here the homogenization actually goes to minus sub-zero level and going to minus 30 minus 25 degrees Celsius, where here in the so these two group of inclusions as indicated by group 1 isocores and the group 2 isocores are plotted here on this superposed on the PT grid for this particular metamorphic evolution. So, we could see here that the first generation of quartz and the fluid inclusions in them, they do pass through the box PT box, which is constructed from phase petrology considerations, and the lower box also has the second this group 2 low density carbonic inclusion to passing through this particular box. So, it becomes very so it is an interesting case of where the fluid, of course, it turns out to be a pure carbonic fluid, not getting into the any much of discussion about what could have been the origin of that kind of a carbonic fluid, but the observation is that there are pure carbonic inclusions, and the one set which are of high density, they represent the peak metamorphic condition, they pass through the PT box representing the peak metamorphic condition, and the second group of low density inclusions also do pass through the lower PT box representing the retrograde metamorphism. So, this there are many such examples, many from different parts, even some work from the southern granulite terrain and the Dharwar Katon they reported, and many other cases of such fluid inclusion work along with phase petrologic work have been presented. And as has been looking at this particular diagram, so if any such situation we do get the fluid inclusion isocores not passing through the PT box defined by the phase petrology either through a prograde or a retrograde path, then we start to think about that what exactly would have happened, what kind of process, and it is of course necessary to see the manifestation in terms of the fluid inclusion morphology, the characteristics, the type of re-equilibration texture that are expected, whether they are present or not, and then accordingly to interpret the data in terms of their correspondence to pressure temperature conditions derived from phase petrology and the ones which we derive from the isocores of the fluid inclusion that we study. So, that brings us to the close of the application of fluid inclusions to different areas of geology. We could cover have some brief idea about applying them to ore forming environments, to deformation. Metamorphism of course could have not been dealt with, but then gives us a very basic idea as to how to go about them, and maybe that if we could possibly look at some more examples in the later in the last week of this lecture series if time permits. Otherwise this provides us to begin with some idea as to how fluid inclusions could be effectively utilized to understand various crustal processes. Thank you.